talk here on signal processing methods for sound recognition. And as you can see from the seminar announcement, that Emmanouil is a senior lecturer and Royal Academy of Engineering Research Fellow at Queen Mary, University of London, and also touring this Alan Turing Institute. Where it is located, by the way?
British Library, the centre of London.
Oh, yeah. Okay, great. So all the rest, and I think that you can read from the announcement, and I don't want to waste his time to talk about the research. And Emmanouil, you also served as the TPC chair of ISMIR 2018, right?
Yep.
Okay, great. Let's put our hands together to welcome Emmanouil for his very first visit.
Okay.
Yes.
Well, thank you for coming, and also thanks to Yi for the invitation to do a research visit at NUS.
Okay. Maybe you could move this. Yeah,
so I think that a lot of you are currently doing some research which could be related to machine learning, deep learning, AI, computer vision, music, sounds, and all that kind of stuff. Maybe on purpose I tried to put the word signal here in order maybe to emphasize some different types of methods that we could use in order to make sense of data, in a sense, a bit more model-driven than data-driven. So this is basically the topic of my talk, is more on how to use information found in the signal itself to make sense of data. Just some context on where I come from. So I'm based at Queen Mary, University of London, where also my former colleague Dorian was based as well. So I'm part of the Center for Digital Music, which is a relatively large group doing work in music and audio technology. We have, I think, 18 academics, 12 postdocs, quite a few PhD students. We have been active in the music information retrieval and sound and music computing communities over the years. And maybe in terms of software, what is mostly well known as an output of the group is Sonic Visualizer, which is an open source cross-platform software for visualizing and extracting information from audio. In terms of the research that we're doing, it's quite interdisciplinary. So we are based in a school of computer science and electronic engineering, but at the same time the group also hosts people with a background in musicology, psychology, acoustics, mathematics, music performance, music theory, as well as computing and electronic engineering as well. My own research is mostly around music informatics, so music computing essentially, and machine listening, which is mostly what I'm going to present today. So using machine learning and signal processing methods to extract information from audio. So the outline of the talk, which should take about 40 minutes, I want to discuss a few things happening in this application area of sound recognition, and specifically about how we can use matrix factorization methods for making sense of sounds, trying to recognize sounds, and some applications later on. So on sound recognition, so that the overall field of my research is machine listening. So the field of study where we try to extract meaningful information from audio. And when we say audio, that could be speech, that could be music, that could be any kind of environmental sound, urban sounds, nature sounds, domestic sounds. In terms of the knowledge required in order to do so, it's mostly a combination of signal processing and machine learning. But sometimes we also incorporate knowledge from other areas such as acoustics, could be psychoacoustics, bioacoustics, musical acoustics, also from perception, cognition, music theory, depending on the application domain. And delving more specifically about analyzing environmental sounds. So any kind of sound that is not just about speech or just about music, let's say. So there's this kind of emerging area which started growing maybe about 4 or 5 years ago. We call it nowadays, we used to call it computational auditory scene analysis. Nowadays it's mostly well known as computational sound scene analysis. There are several problems that are being addressed in this emerging research field. The first one, which is sound recognition, sound event detection, so recognizing sounds. The second one is sound scene recognition, so trying to understand the environment of a recording. Is this a meeting room? Is this a street? Is this a park? Then source separation, trying to separate different sound sources from a single recording. Maybe noise reduction as well. In terms of applications, there's quite a lot of emerging applications happening in the area of, first of all, of just managing sound archives, but also, perhaps more importantly, in smart homes. So all these new devices, Alexa and so on, they are all using some of these technologies in the back end. Smart cities, for example, for urban monitoring, for noise monitoring. Security and surveillance, automated systems trying to infer any hazardous situations from audio when vision is not sufficient to do so. And also acoustic ecology in terms of, for example, automatic biodiversity assessment. So there's actually quite a lot of things happening in this new area, which we call computational sound scene analysis, which is also reflected by this series of workshops and challenges happening, which is called DCASE, which stands for Detection and Classification of Acoustic Scenes and Events, which now happens every year. It's both a workshop and a competition trying to steer interest in this area. More specifically, I'm going to focus the presentation on sound event detection, sound recognition, which is one of these core topics in this area. The main goal is to try to identify labels and start times and end times from specific sound events that occur within an audio signal. And these sounds could be very well also overlapping. So we come out to what we might call polyphonic sound event detection, whereas monophonic sound event detection would be the case where we have non-overlapping sounds that we want to detect. And it is still quite an open problem, especially in the case of really complex recordings where we have many sources emitting sounds at the same time. When you have noisy environments, so there's a lot of noise, this still remains an open problem. So in terms of the methods to be presented today, so matrix factorization, what is this about? So maybe illustrated better by an example. So here you see in the top figure here a spectrogram, so a representation over frequency and time of what I'm going to play now. Sorry. So it was basically 3 beep sounds and 1 door slamming in the end. So you have the beep sound, which is basically like a harmonic sound. You see frequencies and their harmonics. And the door slam, which is basically a noise-like sound. So you have sort of activation in all these frequencies together. So we want to try to come up with a method for trying to recognize these 2 types of sounds and when they occur over time. So one technology that was invented a few years ago was, what if we treat this spectrum as a matrix, as a 2-dimensional representation, and we try to factorize it? So we try to decompose it into 2 factors, and this is the point where I'll try to write down a few things on the whiteboard here. So let's say that our spectrogram is V, so that's, let's say, frequency over time. So we try with matrix factorization methods to come up with a product, to factorize it into a product of 2 matrices, W and H. And the idea being that V is supposed to be non-negative. It's supposed to have non-negative values, and also W and H are supposed to have non-negative values. What this non-negativity gives us is that it tries to express the input that we have here into parts, into specific components, which are all added together. So we have here one image, let's say one representation that contains the alarm sounds, that contains the door slam. So it's basically adding parts of door slams and adding parts of alarm sounds together, trying to come up to represent this. So here this product should have dimensions frequency times a rank, K, and this is also a rank times the time here. So that means that W is essentially what we could call a dictionary of templates over frequency, of spectral templates, which contains the signatures of the unique events that are happening within the signal. So in this case, if we use a K of 2, so a rank of 2, we come up with a W, a dictionary, which has 2 signatures, 2 templates. One is a template for the alarm sounds, so you see harmonics here happening, and one is a template for the door slam sounds, which is a bit more noisy. Likewise, the other matrix H, so that has dimensions of k, the rank, over time. So that tells us each component when it is active over time. So we see here that we have activations of 3 door slams over time. So we see that these are active over time. And we see that towards the end, the second component, which is a door slam, is also active. Another way, to those familiar with neural networks, of expressing NMF could be something akin to an autoencoder. So let's say that we have our input V, and we want to approximate that input. So this is V again. So let's say a reconstruction of V. This is H. And all these weights here are W, a pseudo-inverse. And these weights here are W. The difference between NMF and a single hidden layer autoencoder is the fact that this model is completely linear. It doesn't have any non-linearities. But it's essentially the same thing. So based on this concept, sorry, wasn't meant to do that. There's also a different way of viewing matrix factorization, which is through probabilities. So a few years back, Smaragdis came up with this model called PLCA, which stands for Probabilistic Latent Component Analysis. The idea is that, again, we have the same model of trying to decompose a matrix into 2 factors, but this time viewing it through a probabilistic perspective. So here, we are trying to approximate this input into a bivariate probability distribution over frequency and time, which in turn is decomposed into 2 main components. One is a probability of the frequencies over a specific component, which is our W over here. And the second thing is the probability of the component over time, which is our matrix H over here. The nice thing about having a probabilistic formulation is the fact that we can also plug in a few other methods from probability theory, from probabilistic machine learning, so we can come up with maybe some more interesting models in the future. And these PLCA method, or these NMF methods, have been quite commonly used in many machine listening applications, both on recognizing sound events, recognizing sound sources, separating sound sources, detecting multiple pitches in music signals, and so on. So a few more details now about how I try to use this sort of field of knowledge for my own research in recognizing sounds. So what I wanted to do at the time, also in collaboration with Marc Plambly and people, also Mathieu Lagrange from France, was to come up with a system that was able to recognize multiple overlapping sounds in an office environment. That was the idea. And we wanted the system to be relying on a dictionary. Let's say that we have with us a data set with many samples from different sounds that might happen in an office. Let's say people coughing, door slamming, drawers opening, keys, people clicking their mouse, typing, stuff like that. And the idea was that we wanted to come up with a system that was able to detect all these kinds of sounds. Maybe they would be overlapping, maybe not. And also to have some sort of temporal constraints on the way that sounds evolve over time. That was the main idea. So we came up with a system that essentially took an audio recording as input, computed a representation, a 2-dimensional representation, a spectrogram, used this matrix factorization inspired model with a dictionary, and then produced a series of events to be detected.
Excuse me?
Yep.
Implementation for your spectrogram, it is the magnitude?
Yeah, it's a magnitude.
Long or little long?
In this case, I can specify here exactly what it was, the spectrogram. A bit inspired by auditory theory. A lot of people doing machine learning nowadays use the MEL spectrogram as the default representation. Here we were using the ERB spectrogram, which is basically, it's kind of like quite similar to the MEL spectrogram. It has frequencies that somehow are resembling to some sort of auditory models from psychoacoustics. And we also gave more emphasis to the higher frequencies because they also contained important information for specific sound events that are quite high frequency.
So just a follow-up question.
Yeah.
So is this ERP filter bank clearly better than this MEL filter bank?
Well, at least in this scenario it was. Whether it's better for deep learning applications, that I don't think it has been thoroughly investigated, to be honest.
Right.
Might be useful to do so. But it's actually not too dissimilar, I would say. So the proposed model in the end, so I was trying to expand this original NMF or PLCA model, which only had 2 factors, and I was trying to add factors that would be relevant to the problem I was trying to pursue. So I had in my hands a dictionary of different types of sound events, so all these mouse clicks and door slams, so I had many of these examples from each sound class. So I had this dictionary which had spectral templates, so frequency, here, I had the sound event class, I had the exemplar index, so how many of these mouse clicks I had. I had 20 mouse clicks, so this was the index of my mouse clicks, let's say. And I also had this Q variable, which was the evolution of each sound, how it evolved over time. So the beginning of the mouse click sound, the middle part of the mouse click sound, and the decay part of the mouse click sound, for example. So this was my dictionary, so that was my input, essentially. And here was the main thing I wanted to get out, was a probability of when an event is active over time. And here was also some auxiliary probability, so when a specific exemplar is activated for a specific sound event type, so the S is the sound event type, and here is at which part in the temporal evolution of the sound event are we. So Q is the index for temporal evolution, S is the index for the sound event type, and T is the time index. So essentially I had as input a spectrogram, a dictionary, and I wanted to infer 1, 2, 3 probabilities. And I was also able, because this is a kind of a probabilistic model, I was also able to incorporate some temporal constraints using a hidden Markov model to perform some temporal smoothing. And the nice thing about this method is that basically inference is really quick. It's just a matter of a few matrix multiplications. Can be even done in an embedded device. It only requires a few iterations, maybe 10 or 20 iterations are sufficient. So it's quite fast, and convergence is actually guaranteed to converge as well. So everything works out quite well in the end. So the output still, however, looks a bit noisy. So this is kind of the raw output I get on the system. So this representation here is the index of sound classes over time. We need to convert that into a binary representation to say for sure that this specific sound event is active from this time point to the other time point, which is fine. And at least in that time, it was state of the art when tested in specific data sets that were compiled and recorded in both London and in Paris on scenes in office environments with different complexity. That was fine, but still was not the end. By the way, the code is there in this link if anybody wants to try it. So then the next problem I was trying to tackle is how can we maybe improve on this thing to make it a bit less noisy. So what I wanted to do was to come up with a method that would be able to take this noisy thing and maybe track the sounds over time a bit more elegantly. Ideally, I would like my system to look like this, the output of the system, to be a bit more concrete, to have a clear beginning and the end of all these sounds that are present in my audio recording. So this was, again, a collaboration with Marc and Mathieu and Grégoire to try to track multiple concurrent sounds over time. So the motivation from this work was also a bit on probabilistic machine learning theory. So because I wanted to track sounds over time, so that means that I would like to use a sequential model. And the most traditional sequential model is basically the one where you can have a Markov chain, observations, and the observations are linked with a latent variable, and the latent variables are linked over time. And this is the most sort of basic sequential model. If the latent variables are discrete, then we come up with the quite well-known hidden Markov model, the HMM. If, however, the latent variables are continuous, here the hidden space is continuous, then there's a more general family of methods which are the state space models. And more specifically, there is a particular state space model that's quite famous from for quite a few decades now, the linear dynamical system. Some people might be familiar with this as the Kalman filter. It's a quite sort of traditional technique coming from the 1960s. where people were using it for radar tracking. So it sort of emerged from control systems theory. So it was more on the electronic engineering side of things, but was quite recently that people realized that actually this linear dynamical system, or this Kalman filter, is in fact a state space model, a probabilistic machine learning model, can be expressed as that. And specifically the way it works is that you have observations, you have some observed data, and you want to infer some hidden variables which are linked over time. And the way to do so in a linear dynamical system is that you have the latent variables which are linked over time using a transition matrix A. You have your observations which are linked with your latent variables, such as so, with an observation matrix similar to an HMM, and you also have some noise, a noise for the transitions and a noise for the observations. The good thing about these methods is that they actually support exact inference. So many of these probabilistic machine learning models, they rely on approximate inference. You might have heard of terms like variational bias or macro chain Monte Carlo. So the solutions are often quite computationally costly and not perfect. Whereas in this case, actually inference is exact, which is good. Using a process which is not too dissimilar to the HMM inference process as well. So the inference is achieved using the relatively well-known Kalman filter and Kalman smoother algorithms, which is for the online case where you don't have access to the future, and also for the offline case where you have access to both the past and the future as well. Again, these methods were actually used quite a lot from the 60s onwards for tracking objects. And I wanted to try to use this method to try to translate the output of my noisy system. So I was assuming that the output of my system, the one that was trying to detect sounds, was noisy. And I wanted my output to be ideal. So this was my observation, the noisy output of my system. And this was my latent variable, my latent space, my ideal output. And I wanted to find a method that would translate the noisy system output to the clean system output. And using also linear dynamical systems, this also enabled to have some sort of temporal coherence as well, which was nice. And the fact that the latent space is both continuous and multidimensional meant that I can also track multiple events over time, not just one thing. So the HMM is potentially interesting if you want to track maybe one thing at a time. It's not directly easy to do so for tracking multiple events at a time. Whereas the linear dynamical system is actually able to track multiple events over time. So it was a nice thing. So in the end, we came up with a model that essentially jointly optimized the identification of sound events, as well as was jointly able to track those events over time. So because also the linear dynamical systems are probabilistic models, that meant that was actually quite straightforward to integrate the linear dynamical system part with the probabilistic latent component analysis model that was my core model in the beginning. So everything integrates quite smoothly and nicely, and we're able to get quite good results on this. So that was that. This was just an application of trying to come up with some methods for detecting sounds in office environment for maybe smart office applications or so. That doesn't restrict the applicability of these methods to only this kind of environment. So there's also some work I did in collaboration with my colleague Dan Stowell, who is working in the area of computational bioacoustics, and also Lisa Gill, who's an ornithologist. So it was a quite interesting project where we had access to some jackdaws. So it's a particular bird species. And we put backpacks on those birds. A small backpack in the back of the bird, which contained one tiny microphone and one GPS. And we let the birds fly. At some point, the birds got bored of the backpack and they just put it away and throw it away, something like that. Then we locate the backpack through the GPS. And the idea was that we were trying to automatically infer what the birds are doing, the context of those birds. When they are flying, when they are sleeping, when they are eating, and so on, when they're communicating as well. So the data we had, given the fact that this was low quality microphones, the birds were flying, so there was wind and all that was quite noisy. And there was a lot of painstaking process through Lisa's efforts to identify the context of each recording of each bird. And then we used a similar kind of method for detecting the context of those birds, again using these PLCA approaches, the matrix factorization approaches. Again, so we had the input spectrogram and we tried to decompose it. We had access to a dictionary of spectral templates for different contexts for the bird activities, and we also had access to many samples of this particular context. The main output we wanted to get the probability of a context over time, and we also had an auxiliary probability of the contribution of a particular example of a context over time. So again, we had an output which looks like this. So it has all the different contexts over time. Black corresponds to correctly detected context, red corresponds to false alarm, and blue corresponds to misdetection. So the output is really noisy, because the data also is quite noisy in the end. And we tried also different machine learning methods. This one seemed to be quite good, in fact. And this was still a good start towards trying to explore and to automate a bit the process that is used often by ornithologists and bioacousticians trying to understand the activities of birds. Another more recent paper that was published a couple of months ago by one of my students. So Ines is a very unique combination of a computer scientist and a beekeeper. And she came up with this fantastic project, which was basically trying to understand the context of a beehive using audio. So again, this relied a lot on sound recognition, trying to first discriminate bee sounds from non-bee sounds. We keep only the bee sounds. We throw away any other sounds from humans, from cars, and so on. And we then try to understand the context of the beehive. Is everything good in the beehive? Is the queen about to leave? Has the queen left? Are the bees about to swarm? Is the beehive ill in general? So there's quite a few contexts that can be automatically inferred using audio. So again, we use the similar matrix factorization methods along with other more traditional machine learning approaches to solve this question.
Is there a reason you use MEL now?
So this one we used MEL because we were trying to also exploit a bit on the CNN sort of DNN side of things, so more deep learning research here. So to conclude, I hope to convince you that possibly these tools could be useful for trying to make sense of audio. What I like about these methods is that actually you can interpret what is happening. You can interpret every step of the way, every component. You can visualize it. You can understand it quite easily. You can extend it by your own domain knowledge. They are computationally efficient because in the end of the day, it's just a few matrix multiplications, not too many in the end as well. And of course, they can also be sped up using GPUs and so on. It's easy enough to integrate some basic elements from acoustics or from perception or from any other field of knowledge to come up with a more complex model. They are already in use in several public tools and private tools as well. They are being used in companies, for example, that work on embedded devices that want to do real-time detection of sounds or real-time understanding of the audio context. And they're being used increasingly so for other domains, for music analysis, for environmental sound analysis, for nature sound analysis, and so on. There's still a lot of things to do, both in this particular methodology, but also in more modern deep learning methodologies. One thing that I find particularly interesting is on the potential use of language models. So this is something that happens a lot in speech recognition. So in speech recognition, if you want to develop a system that recognizes speech, you have an acoustic model, which tries to make sense of the audio, but you also have a language model, which tries to use some basic knowledge from grammar, syntax, trying to predict what's going to happen next, trying to disambiguate some words. We could use similar principles to the problem of environmental sound analysis towards modeling periodic events that are happening. So if you have a sequence of footstep sounds, then you can easily predict when the next footstep might appear, for instance. So similar methodologies coming more from the field of natural language processing could be also used for analyzing non-speech, non-music sounds. The other thing, which is quite open, the other topic, which is context-aware sound recognition. So this is maybe a problem which is not limited to this particular application domain, but more broadly is that we very often do not take context into account. Context could be, in this case, the scene, the environment of a recording. Is it an office? Is it a park? Is it a street? But also context can be other things. It could be music style. It could be music that could be tonality, could be key. In speech, it could be language, pronunciation. I think he has worked on that one. So can we use context in order to properly modify, maybe automatically, our systems to recognize better sounds? Another thing which is also quite open, I did show a couple of different representations. There's still an open question on which is the best representation, and maybe some of the more recent machine learning methods can automatically learn interesting representations as well. And the last thing, because it's a kind of a new area, there's still not a lot of agreement on the taxonomy of all the sounds. Which sounds how can we organize sounds, in which principles, which ones are more interesting, how can they be divided, is it going to be a tree-like structure, is it going to be a bit more messy kind of way of organizing sound events? So this is quite open yet. If anyone wants to learn more about this community, I would just recommend to visit this website. This is the website for the DCASE community, the Detection and Classification of Acoustic Scenes and Events community, which organizes a yearly workshop and a competition. The competition started a few years ago from Queen Mary, and it has now evolved. It's a cross-institutional competition, which is now led by Tampere University of Technology, where also Yi spent quite a few years there. And that's it. This is not just about my own research, it's also all these people's research, and thank you very much for listening.
Can you say a few words about how you determine the rank and things like that?
Yeah, there are methods for automatically determining the rank. However, we mostly use this in a supervised scenario, so we know the rank beforehand. So if I want to detect 10 different sound types, my rank could be 10, basically.
So it's easier to reinterpret the correlations.
Yep.
Okay. Any questions from the audience?
Can this be used for linear regression kind of things where it's not specific classes, it's a continuous output variable?
So the rank has to be discrete, but the actual matrices, of course, are continuous by definition. So yes, and the thing is that basically H is a non-binary mid representation, so it's essentially a regression output. You could view it as a regression output.